Yeah, thank you very much for giving us the opportunity of presenting light fields. My presentation today is called Light Field in the Wild. And I think Lars just really gave a good introduction to the field, especially when he talked about compact sensors and at a good price. I think this is exactly what we are talking about. But more than that, I want to focus on what we're doing in terms of light field technology and artificial intelligence for sensing, vision-guided robotics, and quality inspection. So let's see. For those of you that are not fully aware of what we are doing at HG Vision Systems, so we are founded in 2017. We are like a powerhouse in the heart of Germany, in Heidelberg, and we are 14 experts in the areas of machine vision, robotic kinematics, software development, and engineering. And of course, as you do nowadays, we have won a number of prizes with our key technology that we are working on. So I've said I want to talk about light field technology. What we are doing is a little bit special in that we're using discrete sensors for capturing the light field. I'm sure that there are a lot of experts here in the auditorium so that you have a basic understanding of what light field imaging is doing and what the advantages are. Yet I want to give a small introduction to the field and then also show you what's unique to our sensors and our technology. So basically, in standard computer vision, you capture an image, you do some processing, and either you view the image or you do some other processing afterwards. In light field capture, it's a little bit special in that we not only capture an individual image, but you can capture the light field, which is basically not only the gray value information from one location, but it can be thought of as capturing information about a scene from all types of directions and in different modalities. And basically, this can be done as a lot of you might know from Lightro, which was a US company. They put in a micro lens array between the lens and the sensor, and this allowed them to capture the scene from a little bit different viewing angles. So what you get then is, as you can see here in the center, you get kind of an image composed of a lot of sub-images. And then in order to see the what has been captured, you need to do some processing. And so this is kind of what is termed the field computational photography. And it has a number of advantages. So just to give you an example, here's such an image as you might recover from such a microlens system. And although you might get an impression what to see, we need to do some computation in order to get the right image. And of course, then the question is, why would you want to do that? Why don't you just capture an image as you usually do? Well, the nice thing is that you can do a lot of things after the fact. So in normal photography, you have to think about where do you want to capture the image, what should be the area of focus, for example, and later on you cannot change anything anymore. And that's the nice part about light field imaging. We capture a lot of data and then we can do a lot of interesting things afterwards. So for example, here is you might see that we can change the viewing angle after the fact. Or we can change the focus after the fact. And all of this is possible just using light field capturing and light field processing later on. If you look at the original capture, you can see immediately that there's a little bit of a drawback of this type of technology. And this is basically that we have an optimization that we have to perform between the area of each of these individual micro lenses. So how small is your field of view that you're getting, or how big is the area of different light rays entering the system. And this is something that we have addressed by using discrete cameras, discrete sensors. There we have a really high resolution of each of these views, and we can change, depending on the application or depending on what you want to achieve, we can change the location of this camera, and this gives us the best of all worlds for a specific application, basically. Another thing that this can be used for is, of course, not only generating images, but generating 3D data. So because of all the light field imaging that, or light field data that we capture, we can later on reconstruct a three-dimensional scene. And this has some distinct advantages as compared to standard technology. If you think about normal stereo approach, and stereo can be either two cameras, as seen in this illustration, but it can also be just a laser projector and a camera. So basically everything that you've heard before when we talk about 2D or 3D capturing devices. And if you want to have a good resolution, then usually you have to move the two cameras further apart. So we are talking about a larger baseline. And this then increases the accuracy. But at the same time, if you have a complex scene, then you get all kinds of occlusions. And all of a sudden, you don't have a dense image or a dense depth map anymore. This can be circumvented with our light field capturing system. So we are using discrete cameras. And because of the light field imaging, we have a really, really high resolution. And this leads to a really small and compact sensor. And usually we don't have a big issue with occlusions, or we can definitely have a much larger capturing area and have a higher resolution of data. And of course, data is everything nowadays. We can use this high resolution of data for vision-guided robotics, but also for quality inspection. The light field is more than only 2D and 3D data. It also allows us to really discriminate the surface properties of an object. So this is shown here. Usually, if you have a 2D image, then what you see is the geometry of an object, but also the color information, and superimpose the glossiness. So if you have metallic or plastic objects, then very often you have glossiness, and this leads to difficulties in stereo approaches, for example. And in the light field imaging, the nice thing is that we can really discriminate between geometry, color information, and glossiness. So we get basically 3 channels of data as the output of our processing. And this allows us to capture really high quality 3D data. But at the same time, we capture the color information, the texture of surface without the glossiness, or we can analyze the glossiness. And this is really a lot of information for quality inspection. So our first sensor, our first product is what we term LumiScan X. It is a really small and compact sensor. It's about 10 centimeters in size. It's composed out of 1.2 megapixel cameras, 13 of these, and we have it takes us about 50 milliseconds to compute a full point cloud of a meter in volume, and the set resolution is generally 0.5 millimeters at a distance of 1.5 meters, but this can be tuned, of course. The nice thing is it's very flexible. It's a passive sensor, so it just uses round illumination, and it can be deployed on the robot or off. And it's a one-shot solution. So basically, we capture an image stream of 3D or of this light field information, and this can be used for recording motion on or off the robot. We have used AI processing on the raw data together with a neighboring company, Revit AI. This has been published in Vision magazine lately, and basically shown here is a 3D point cloud as derived from the sensor. So what you can see is that it's a very nice quality. These are difficult objects. We are looking a little bit from the side so that you get a good impression of the 3D data. And you can see we have a really, really high and dense point map. This includes AI processing. So very often you want maybe to be on the safe side and use it together with classical models. And this is superimposed here. So the yellow data is the point cloud from light field imaging, which is just capturing information at the texture or the borders of objects. And you can see here also the very high quality of this data. This is very fast processing, and this is superimposed with the AI processing as shown before. So you can have the dense point cloud for doing all sorts of object recognition tasks, but you can also use the only the borders, like in event-based vision, where you have kind of only the relevant information for object borders, for example, which can also be used for vision-guided robotics very efficiently. Okay, I talked about light field imaging in the wild. So it's not only our sensor, the LumiScan X, but we have also developed a complete software suite for using this data So basically, we term it LumiScan VGR, which is vision guided robotics. And this is has the full information that you require, from capturing the data to handling the robot, doing collision checking and object detection, of course. And this is done in conjunction with AI. For example, for automation in challenging environments like an auto store here. And this just shows you one of our partners where we deployed the sensor. You can see it here hanging over the scene. And we can use it, as I outlined, for really challenging materials. And in this case, it's packaging of aluminium foil, for example, to a very high accuracy. So the objects that we are detecting are detected with an accuracy of 0.1 millimeters, basically. And this is fully AI based, so we do not know what parts are coming. This is due to the processing of our customer, but we only detect where the objects are located within the packaging. This is very important here because the handling has to be done very precisely in order to place the part later on. This is done with an orientation, of course. And at the same time, we have multimodality. So for example, we can measure mud labels at the same time and so on. We can have different packaged reels in this case, for example, and we need to enter this hole that's shown on the left-hand side of the reel to really high accuracy of 0.1 millimeters, so that the gripper can handle the part, even if it's heavy, as in this case, very precisely. Okay, so this is a glimpse of our software. We do the whole automation. Basically, we are agnostic to robots. Most robots are included in the software already and can be used. Let's switch to the next thing. I mentioned that our camera or our sensor can be attached to the end effector of the robot. This is shown here. So this is in harsh environment of a forgery. And again, the software can be used, sensor and the software can be used for precise object handling. So in the software, we have a nice user interface where you can look at collisions or possibilities of collisions. You can see the detection of the objects, which one will be gripped next. And this is done in 2D and in 3D, depending what is required. I think we should probably, it's maybe interesting to mention, as this is a passive sensor, we can attach, there's no limitation of the number of sensors that can be used in conjunction or together. And we can address as many robots with the same software as you require for the automation. So it's very flexible and has no inherent limitations, basically. Okay, I mentioned the same can be used for quality inspection. So this is an application where the sensor is used also in a forgery for quality inspection of metallic objects. So keep in mind that particularly for glinting metallic objects and or plastic materials, the sensor is really optimized because in the light field, we have all the information we require for detecting texture, the glossiness, and the 3D shape of objects. And this is used in this case for performing a quality inspection. And this is done really quickly. As you can see, we have about 3 seconds, including the handling of the robots. And the nice thing is that we can use the LumiScan X, as I showed you before, as is seen here. But we can also construct an array of higher resolved cameras. So the same technology and the same software can be used for higher resolved sensors. And then it's feasible to measure much to a higher degree of accuracy than this sensor can. So we don't have really hardware limitations. That is really the nice part about the this type of sensor and the technology behind it. Okay, what is this? The software can be used not only for quality inspection out of one view, but we can use it for capturing complete 3D objects. So in this software, we can position the sensor relatively to a CAD model, for example. And then in the first step, the object location is detected. And then the robot or the sensor, which is attached to a robot, can be automatically be positioned around this object relative to the object so that we can capture the same parts of an object and inspect it for quality. So this is really important to our customers that have a high variety of objects or that do not want to have a precise positioning of the objects, but you can just have it on a conveyor belt, for example, and then go around the object with a robot, measure all relevant passes, relatively, or in this case, absolutely, and then do a AI-based quality inspection of the 2D and 3D data of these objects, and then act accordingly. So is there anything? So here you can see the point cloud, for example, of the object, and you can see that we can stitch together a fully 3D point cloud of these objects and then perform a quality inspection on these parts. Okay. It might be interesting to you to learn that our technology is is running on the edge, basically. So we are partnering with robotics, so you can use their hardware for performing our computations. So the quality inspection is done directly on the Control X platform, for example, or on an IPC. We deploy the AI models directly on the system, but our customers can train their own models, either using our software or their own. And we also deliver our software for data annotation and training to be used on site. So this is not a cloud-hosted system, but it can be done on-premise by the customer so that they have their own data and are sure that this is not being used for anything else. So we have a large number of customers, mainly from the automotive industry. This is a small section out of these. And we are mainly working with integrators that use our technology to solve application needs for the end customers. And out of these, there's, for example, to mention, some of them. We are still looking for additional partners and distributors. And this is basically the call to action of this presentation. So if you are interested in what you've seen, you have some challenging applications, or you want to become a solution partner or distribution partner, then get in contact and we can talk about possibilities and also show you what this technology is all about. So thank you very much. And I'd be happy to answer any of your questions.
Okay, thank you, Christoph. Yeah, we have questions. What kind of frame rate is possible with point cloud rendering of 3D views?
A very, very interesting, very good question. So basically, if we're using the sensor I've shown you before, then limiting is not the rendering of the data. Limiting is the data transfer. So basically, we are transferring all the light field data to an edge device on which we are computing the data. This is done in CUDA, so on a NVIDIA graphics card. So this is really, really quick and no limitation. But the slowest part is the data transfer. And our current sensor uses 1 gig Ethernet. So this allows us to compute at 6 frames per second. But if we have also the possibility, as I mentioned, to use other sensor technologies, so other systems with a higher bandwidth, and then we can go up to 5 times this, basically.
Okay, maybe one more question. How do you calibrate your light field camera to achieve distortion-free and metric data?
Yeah, also very good question. So we are calibrating we are manufacturing the sensors here in Heidelberg, and we are also doing the in-house calibration. So each of the sensors is calibrated to a really high accuracy, and this does not have to be done by the end user. So this is all done in-house over here. And then what the customer only needs to do is to do a hand-eye calibration between the sensor and the robot, which is customary in the field. And for this, we also supply very easy-to-use tooling to perform a high-quality hand-eye calibration and get feedback at the same time if what the accuracy expectation is from this calibration. And this can be done fully automatic. So some of our customers use this regularly in their production process just to be sure that they always have the highest accuracy.